This is Pre-Calc 12, section 11.1, and we're going to split this section into two parts. I'm going to call it Permutations Part 1, and then we'll of course have Permutations Part 2. So to get started with this idea of permutations, I want to just bring out an example here. Okay, take a look at our lovely catering class. They're going to have a year-end lunch special menu, and the menu consists of a main dish where you can choose lobster, beef or chicken, and then as a side dish you can choose, salad, fries, rice, or baked potato, and then for dessert you've got two choices, yogurt or pie. So to make a meal, you're going to have to choose one from each of these courses. So one main dish, one side dish, and one dessert. So if I said if one item is chosen from each to create a meal, find out how many different meals are possible by, and I'm going to ask you to list them out. Okay? So you do whichever method you like. I'm kind of lazy, so I'm just going to use lobster, beef, and chicken like that. How about salad, fries, rice, and baked potato? And then I think as the dessert, yogurt or pie, Y and P. So here's me. I'm hungry. I'm going to choose something. I guess I could choose lobster. I could choose the beef, or I could choose the chicken as my main dish. Now, if I chose lobster as my main dish, what can I choose as my side dishes? You're right. I've got the salad, the fries, the rice, or the baked potato. I think the same thing for beef, right? Same four choices. So salad, fries, rice, baked potato. And then I think same thing for chicken. So salad, fries, rice, baked potato. Okay. And then now if I were to follow this path, which is the lobster and then the salad, I guess from there I could have two choices for dessert. You got yogurt or pie. And it's the same two choices for all of them. So YP, yogurt pie, yogurt pie, yogurt pie, yogurt pie. Hopefully your notes have a bit more space than mine. Sorry. Yogurt pie, yogurt pie, yogurt pie, yogurt pie. So doing this, my question now is if you were to count up all the different pathways from me to the end, how many different pathways would you have here? And if you think about it and start counting, I guess what we have is, let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So the idea is to count the number of pathways. And what we have here is 24 different meals. Not bad, eh? 24 meals. Cool. Gee, that took a while, and I'm getting kind of tired with drawing. So, we know the answer is 24 now, but my question is, how can you determine the number of possible meals without listing them out? Let's just quickly take a look back, okay? For the main course, how many different choices did we have? Well, the main course was in red, right? And we had how many choices? Yeah, 3. And then we had our side dish, didn't we? Yeah, side dish. Well, how many choices do we have for that one? Yep, 4. And then for dessert, we had 2 choices. 2. Okay, so looking at those numbers 3, 4, and 2, what do you think I need to do to make the number 24? Okay, use your sleuthing skills and see if you can figure this out. 3, 4, 2, and 24. If you guessed multiplication, because 3 times 4 is 12 and 12 times 2 is 24, you win. You're right. Congratulations. What do you win? You win the next task. And the next task is to fill in this little scroll. It says if one task can be performed in m ways, okay, so that's the number of ways. So, for example, the main course could be performed in 3 ways. And a second task can be performed in n ways, so the side dish can be performed in 4 ways. Then the 2 tasks together can be performed in m multiplied by n number of ways. Okay, and in the previous example we had 3, so you can go m, n, and o perhaps, right? O ways for the third item, and then of course the same idea would exist, you just multiply all of them together. This idea of multiplying them all together is called the fundamental, because it's very basic and elementary and very important, counting principle. Okay, this will serve as the basis for what we do in part 1. So keep this in mind, okay? You're just looking for the number of ways that something happens, and then you do that for all the other tasks, and then just multiply them together. Okay, so let's take a look at example number 2. Got a multiple choice test. Ooh, you guys like those. 8 questions. Ooh, like that even better because it's short. 5 possible answers. Ooh, maybe you don't like that. Okay, now suppose students answer each question by guessing randomly. Of course, you're not that kind of student because you wouldn't be in my class if that's the case, but let's say you were. The question is, how many different patterns are possible for the answers to the 8 questions in the test? Like, could it be A, B, C, D, E, A, B, C, D, or, you know, A, or A, B, B, C, D, you know, what's going on? So if you think about it, in the previous examples, we had 3 decisions, right? We had main course, side dish, and dessert. Well, here we have 8 questions, so we kind of have like 8 decisions, right? So I like to do this. I like to draw these lines. 1, 2, 3, 4, 5, 6, 7, 8 decisions. Now, with the first question, these are questions, I guess, right? 8 questions. So for the first question, how many different possible choices do I have? Just like how in the main course over there in the previous example, how many choices did I have? You're right if you said 5, because it's A, B, C, D, E. Well, how about for question number 2? It's also 5, right? Question 3? Also 5. Get the idea? Yeah, 5, 5, 5, 5, 5, 5, 5. Well, that's the number of ways for every individual task, and then by the fundamental counting principle, I better multiply them all together. So that's the same thing as just 5 to the power of 8. What's 5 to the power of 8? Not too sure. I'll put on my calculator. 5 to the power of 8. That's a whopping 390,625 different patterns. Kind of hard to guess and get perfect, hey? Yeah. Alright, let's move on to page 2. Some other types of questions. Good old Canucks. Well, they're maybe not so good anymore, but whatever. Okay, they're still the home team. So they're playing the Flames. Sorry if you're listening in Calgary, but your Flames are worse than the Canucks. Okay. The score at the end of the game, meaning no overtime, so after 3 periods, was 5-2 for the Canucks. Yay! Go Canucks. So the question I have for you is, how many different possible scores would have been possible after the second period? Meaning, if I didn't watch the game, okay, but I knew at the end of the game it was 5-2, what could the score have been at the end of the second period? Okay? So I guess we can start listing them out. 1-1, 1-2, 3-2, all that kind of stuff. But it's nice to know if we can figure out the number of possible choices, okay, for each of the situations. So I guess my question is, well, we've got 2 things. We've got the Canucks score, right? And we've got the Flames score. Let's do the Flames first because it's easier, okay, smaller number. If they scored 2 goals in the game, at the end of the second period, how many goals could they have scored? I guess they could have scored none, right? Which means all the goals happened in the third period. I guess they could have scored 1, or they could have scored 2. Could they have scored 3? No, because the final score was 2 for the Flames. So how many choices are possible here? That's right, 3 choices. So I always put down the number of choices in the blank. How about the Canucks? Well, I guess they could have got 0 and scored 5 goals in the third period. Highly unlikely, but possible. I guess they could have had 1, 2, 3, 4, or 5. So in this case, 6 ways, right? 6 choices. Well, we've listed them individually. What does the fundamental counting principle say? Yeah, let's multiply them. So there are probably 18 different possible scores. Okay? All right, let's keep going. Okay. Another example here. Oh, we can talk about creating numbers. How many 5-digit numbers can be formed using these digits? The 1, the 3, the 5, the 6, and the 8. Now here I'm going to do a little something different. I'm going to show you what's the difference if I allow repetitions, meaning you can repeat the same number every single time. And what happens if you don't allow? Let's say once you've picked a number, you cannot use it again. Things change. Take a look how. A 5-digit number means there are 5 spaces. Okay. Now, if repetitions are allowed, my question to you is how many possible choices do I have for this first placement? Well, I can choose from 5 different numbers. Correct. What about the second one? Yeah, if repetitions are allowed, I can choose 5, like I have 5 different choices, and 5 different choices, and 5 different choices. So how many choices do I have? 5 to the power of 5. This one I do know. This is 3,125 ways. A lot. Or maybe I shouldn't say ways. I'll say different numbers. Now, the next question is more interesting. Repetitions not allowed. Still 5 spaces, but let's see what's going on. All right, let's take a look at the first one. Okay, how many choices do I have for the first digit? 5 is correct. How many choices do I have for the next digit? Now remember, once I've chosen one of them, it cannot be used again. That's what it means when repetitions are not allowed. So how many different possible choices do I have here? If you said 4, I'm happy. And then how about the next one? If you said 3, I'm ecstatic. If you said 2, yeah. And guess what? There actually is no choice for the last one. You only have one number left. You have to choose that one number. And once again, fundamental counting principle, let's multiply them. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. So 120 different ways. Significantly less than if repetitions were allowed. Okay? Now, this above product here is really special because when you see a number, a whole number, multiplied by the preceding whole number and the one after that and one after that, and it has this pattern of going down to 1, there's a new notation that math people use to represent that. And this can be abbreviated as 5. Don't say exclamation mark or 5 with emphasis. It's actually called 5 factorial. So when I give you that factorial, I'm saying take that number and multiply that number by all of the previous whole numbers, okay, down to 1. So if I had 10 factorial, it would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. In general, if I have n factorial, which n stands for any number or natural number, you start with n, of course, and then you multiply it by the one just before it. Well, the one just before it is times n minus 1. And you multiply by the one before that, n minus 2. And the one before that, n minus 3. And you do this forever and ever and ever until you get to the bottom, which is 3 times 2 times 1. Okay? By the way, this type of arrangement of objects in a row, like what we did in examples 4, and I guess even example 3, is called a permutation. Okay? Where the order actually does matter. Okay? So let's take a look at another example here. Same example, just a different part. What happens if the first and last digit must be even? Okay, so When there are restrictions, we have to deal with that too, okay? So repetitions are allowed. So 1, 2, 3, 4, 5. I guess I should think about how many numbers are even. Let's go back up there. 1, 3, 5, 6, 8. 6 and 8 are even. Okay, so I know there are two even numbers, the 6 and the 8. Okay, so this has to be even. This has to be even. So how many even numbers are there for me to choose from? 2. So I guess there's 2 possibilities here. Now, because I already chose one of them there's only one more even number remaining that has to go in the last spot. So there's only one choice there. Well, what about the odd numbers then? Well, it says repetitions are allowed. So does it matter what type of number is here? Right? This could be even or odd, right? This could be what? Even or odd. This could be even or odd. And repetitions are allowed, so I guess it could be any of those numbers, meaning 5 possible choices for each one of those spaces. 2 times 5 times 5 times 5. How about... Oh, what am I talking about? What am I talking about? Mistake. See my mistake? Yeah, this should be 2, right? Repetitions allowed. Repetitions allowed. So 2 times 5 is 10. 10, how about 500? 500 ways. Sorry about that, okay? But once again, repetitions are allowed, so I could have even numbers. I can use it again, okay? I was getting ahead of myself with the even part, because now over here, repetitions are now allowed? No. Are not allowed. Oops. Not allowed. Okay? So in this case now, we have that example where we have 2 even numbers, and now we can only have 1. Okay. Now what about the numbers inside here? Well, since we used up both our even numbers, I guess that remains is they must be odd. So how many odd numbers are left? Well, yeah, there are 3 of them, right? Now, is it 3, 3, 3? No, because repetitions are not allowed. So remember, once I've used one of the odd numbers, it's gone. So there are only 2 left for the next spot, and there's only 1 remaining for the final spot. So now, if we were multiplying them all together, 2 times 3 is 6. 6 times 2 is actually 12. So once again, we significantly cut down the number of ways. Ouch. Okay. All right, let's keep going. Another one here on page 3. Oh, how many 3-letter permutations can be formed from the word maths? Meaning, let's take from the letters M, A, T, H, S, and I only want you to pick 3 of them. Okay? Order matters here. So, first part, how many different possible choices do you have? Well, there are 5 different letters to choose from, so 5. Then, once you've taken 1 away, you only have 4 left, so that's 4. Take another 1 away, that's 3. So 5 times 4 times 3, that's 60. So 60 different ways, or permutations, when I'm allowed to choose 3 letters from a group of 5 letters here. Now, in this situation, once again, you are trying to find out the number of arrangements possible when taking 3 items from a set of 5 different items. Okay? Now, let's see if we can write this out in factorial notation. Now, remember how we have 5 times 4 times 3? Well, how is that like factorials? It's kind of like a factorial. It's kind of like 5 times 4 times 3 times 2 times 1, right? But what do we not have there? We don't have the 2 times 1. So in order to kind of get rid of that, I'm going to make this into a fraction and put 2 times 1 on the bottom. Because then the 1's kind of divide out and the 2's divide out, and I'm left with the 5 times 4 times 3. But this is important because, look, what is the actual numerator as a factorial? 5 times 4 times 3 times 2 times 1 is a 5 factorial. What's the denominator as a factorial? Yeah, that's 2 times 1, which is 2 factorial. So ultimately what you've seen here now is if I ask you to do if you're taking 3 items from a set of 5 different ones, in factorial notation, the answer is just 5 factorial divided by 2 factorial. Okay? And this is a special type of permutation from the situation from above, and that's why they have another scroll here that you need to know for part 1. It says the number of permutations of n distinct objects, so like in the previous example, 5 different or distinct objects taken r at a time, which would be 3 at a time, is given by this notation, which is called npr, and the formula is n factorial over n minus r factorial. So let's see if that works for above, okay? In our situation, once again, we were taking 5 distinct objects, and we were going to take 3 at a time, okay? Using the formula, that becomes 5p3. Remember, the first number before the p is the n, so this becomes 5 factorial. And then n minus r would be taking the 5 minus 3 and putting a factorial sign. And the 5 minus 3 does give us a 2 on the bottom, which is great because that matches up with what we had before, and the formula works. Okay? Please memorize this. You're going to use it quite a bit. Okay? It says we can always use the formula to solve factorial notation questions, and I want you to just make a quick note. If you ever run into this idea of 0 factorial, the answer is actually not 0, but it's defined as 1. Okay, so all the other factorials make sense, right? Because you're multiplying them all the way to 1, but 0 doesn't. So by definition, by convention, 0 factorial is equal to 1. Okay? All right. Student government. Elections should be coming soon, I think. Student government has 3 executive positions available: president, vice president, and treasurer. You can only have these titles if you're already part of the 8-member student government group chosen by the school population. So you get chosen to be a part of the government first, and then they choose individually. So the question is, how many different ways can these 3 positions be filled? Now notice these 3 positions are totally different positions. Okay, so if I was chosen as president, that's different than me chosen as vice president or me chosen as treasurer. So once again, this is a permutation. So you should ask yourself, how many objects do I have, or how many people do I have, and how many am I choosing? Yes, it seems like you have 8, right? So n equals to 8. You have a group of 8 individuals, and you want to choose 3, so r is 3. So you can plug into that formula, so that'd be 8p3. And sorry, if you're not too sure what formula I'm talking about this one. npr n factorial over n minus r factorial. Okay. So we have 8p3, that's 8 factorial, divided by 8 minus 3 factorial, and 8 minus 3 is 5 factorial, 8 factorial, and you're thinking, how am I going to solve this? Well, watch. 8 factorial, and you can do this without the calculator, times 6, times 5, times 4, times 3, times 2, times 1. 5 factorial is just 5 times 4 times 3 times 2 times 1. Well, guess what? Cancel or divide. You're just left with 8 times 7 times 6, and that's just 336 ways. Okay? So it does it for you like that. And by the way, if you're actually curious about your graphing calculator, if you have one, yes, it does it too. I'll quickly show you. You type in 8, and then you press Math, and go over to PRB, which is the probability stuff, and choose number 2. 8 NPR, and then put the R afterwards, which is the 3. Press enter, and you'll get 336. Ta-da! So your calculator actually calculates it for you right away. Okay. As a quick exercise, you can try the next one here. And how many ways can 5 students from a group of 9 be seated in a row of 5 different chairs? So I'm going to ask you to stop the tape right now, or stop the video, and try it. Shouldn't take you too long. Come back and double check your answer with me. I got 15,120. If that's what you got, we're both on the same page. Let's move on. Okay. You might be thinking, Mr. Lee, so why do I even need that formula? Because, hey, I've got the calculator. Well, here's how you need the formula, because I'm going to ask you to write out these expressions. Okay. I want you to write out these expressions without using the factorial symbol. So I want you to write them out using n, okay, as an algebraic expression. So remember that formula again, NPR equals to n factorial n minus r factorial. So using that as our guideline, let's do A, which is NP3. I say n factorial over n minus 3 factorial. And you'll be thinking, how do I simplify that? Well, remember how n factorial is just equal to n, and you multiply it by all the previous numbers. So I guess it's n minus 1, then n minus 2, n minus 3, n minus 4. Now the question is, man, how long do I write this out for? Forever, until 3 times 2 is 1. But wait! Can you see how the n minus 3, n minus 4, and everything else after this is equivalent to n minus 3 factorial? Now, why is that important? Well, because on the bottom, I also have a n minus 3 factorial. So, what I'm saying to you is all that stuff afterwards just kind of cancels out. This and this cancel out. So you're just left with n times n minus 1 times n minus 2. And to try to speed this up, I'm going to multiply this out. So n squared minus 3n plus 2. And then we'll distribute the n. And I think we've got our answer. N cubed minus 3n squared plus 2n. And it's as simple as that. Okay, so why don't you try part B? It's the same kind of idea. All right, I'll work it out here, but I don't want to say anything because I don't want to ruin the fun for you. So for those of you who don't want to listen, then don't listen. Those of you who have no clue, then yeah, take a look. But once again, don't just blindly copy because you're not going to learn as much that way. Try it out on your own first. Okay? You have nothing to lose. No one will know if you can't do it. You're sitting by yourself at home. Geez. Maybe your dog will know. Okay, let's go. What's the next number before preceding n plus 1? I'm going to subtract 1, so n plus 1 minus 1, that just gives me n. And then you have n minus 1. And then look, n minus 2. So guess what I'm going to do? I'm going to stop here at n minus 2 factorial. Because, like I said, every single term after that being multiplied, what a waste of time just writing it out. That's just n minus 2 factorial. Which means that, perfect. Divide out. Nice. I'm going to just regroup this a little bit because it's going to be easier if I put the n in front and the n plus 1, n minus 1 together. And then the n plus 1, n minus 1 part here is, what is it? Oh yeah, difference of squares. And then we can just simplify. We get n cubed minus n. Ta-da. Alright, example 8. You're going to have to know how to solve questions too. So once again, using that formula, you're going to try to do this. So let's simplify first. NP2 is just n factorial over, I think, n minus 2 factorial. Once again, write out the terms. N minus 1, n minus 2. I'm not going to go any further because I see the n minus 2 factorial on the bottom. And that's great because they cancel out or divide out. Going to distribute that in. So n squared minus n equals to 30. Oh, a trinomial in our midst. Oh, can you say factor? Say it. I didn't hear you. Louder. Okay. Find two numbers that multiply to negative 30 and add to negative 1. Guess that's n minus 6, n plus 5. So here we have it, n equals to 6 and n equals to negative 5. Leave your answer like this and I'd be like, because guess what? N has to be a natural number. Say goodbye to negative 5. This is what we call an extraneous. extraneous root. In this case, of course, is just n equals to 6. Okay? And you can try that out on your calculator. 6p2, that's 30. Alright? B is a little bit different, so let me show you that too. Okay, this one's a little bit different because I give you the n, but I don't give you the r. So using the same formula, it'd be 9 factorial, 9 minus r factorial, and here's our dilemma because we don't know what the bottom simplifies to. But what we do know is we have a number on the right-hand side, 504, and since it starts with 9 factorial, there probably is a factor of 9 in 504. So if I were to actually break up 504 and divide, let's say, it by 9, turn on calculator, 504 divided by 9 gives us 56. Oh yeah. Well, 56 is the same thing as 8 times 7. So I've already now rewritten 504 as 9 times 8 times 7. Well, it looks like it's 9 factorial, but it stops at 7. So what must the bottom be? Well, I guess that bottom must be what? So if it stops at 7, then I think then the denominator, I'll say therefore the denominator, 9 minus r factorial, what must that number be? Yeah, that must be 6 factorial because that's all the stuff that got canceled afterwards. So if 9 minus r factorial equals to 6 factorial, then I guess that means that 9 minus r must equal to 6. So what's r? Yeah, r is just 3. Okay? That's how you do that. Alright, and example number 9 is a little bit just, I guess, for fun, so I'm not going to ask you to do that, but if you want to, you can. It says show that the left side equals to the right side, and how are you going to do that? Well, you may want to factor, so I'm going to give you a hint, because look, there's an 18 factorial there. How about factor an 18 factorial from the left side, okay? And then figure it out from there. Alright? If you're not too sure how to do this, come ask me in class, but I don't think it's too hard, okay? Well, here, I'll give you one more hint. What's 20 factorial divided by 18 factorial? Well, that'd be 20 times 19 times 18 times 17. Oh, wait a minute. All that stuff over here is just 18 factorial. So that must cancel out with the bottom. So that first part is 20 times 19, okay? You figure out the rest and enjoy. See you for part 2.